Hi everyone, I'm Deepak Pathak and I am currently an assistant professor at Carnegie Mellon University in Pittsburgh. And sorry that I could not attend RSS in person, but I'm still grateful to have been invited to this workshop. So today I'll talk about the role of adaptation and continual improvement in robot learning. So before I do that, let me start with the goal or the context with which our group works in. So the focus in our group is towards this grand goal of building general purpose embodied intelligence. Now, what do I mean by that? In some simple terms, is for robotics, robots that can do thousands of tasks in thousands of environments. So building agents that are not good at only doing one thing, but can do a variety of tasks, like from cleaning your house to laundry, but not just your house, but everyone else's house out there. This goal is very far from where things are today. Like today, we have systems that work very well in the same task in same kind of environment settings. So for instance, although we have seen stark progress using reinforcement learning in a variety of complex tasks, but these systems are specifically focused to what they are trained for. For instance, if I train a system to play the game of Go, I cannot usually transfer that system to also go and grasp objects from a table. But this problem of generalization or from one task or from one example to others is not specific to robot learning. This is there fundamentally in deep learning and in more generally AI. So to give you an example, if you take the simplest case of supervised learning, like where we can train a deep network to take a bunch of images and output certain class, these models work really well. Like they obtain superhuman accuracy on the test set of ImageNet. And here, this is a result from ResNet 50. But if I take this model and I try to generalize it beyond ImageNet to not very far to a video from YouTube, this model finds things like cobra snake. In one frame, it thinks this is a ray fish. In another frame, it thinks this is a flatworm. Now, this is a real result. This is ResNet 50 output across different frames of these videos, while just testing slightly out of distribution from what it was trained for. Now, this ResNet 50 is, I don't know, like 5 to 6 years old. So at this point, people may argue that transformers, new techniques and randomization and all that may have potentially addressed these issues. So what I did, I fast forwarded this result for 5 years and I downloaded the latest transform model, the vision transformers, and I test this on an image shown here. Now, all of you may recognize that this is a chair, but if I pass this image through this latest vision transformers, it classified it as a band-aid. Now, if you look at from it far enough, you can see why is it a band-aid, like it has this dots, etc. But look at the confidence on being wrong of this model. This is super high. Now, what is the main reason here? So the main reason in these failures is as follows. Like in machine learning, whenever we start, we assume the assumption that the data in the training set, data in the test set, they belong to same distribution. But in reality, this is not true. And whenever this is not the case, things start to break. So for instance, chairs in ImageNet look like this. But if you see chairs on a robot in a real world, they look something like this. So it's very difficult to generalize and transfer beyond these scenarios. And this problem is much worse in robotics. For instance, in robotics, we have systems that can do one task really well, but it's very difficult to transfer them to do a simple task of putting a block on the table. But unlike misclassifying a dog to a cat or something, or chair to something else, every failure in robotics costs physical money, and so it's bad for the hardware as well. So the problem of generalization in robotics really boils down to this question. The question is, how do we generalize beyond training scenarios? And like the argument in our group, or the argument that I believe in, if we truly want to generalize beyond training, there is only one way. Like we have to figure out how to keep adapting. So like what I'm arguing against is this current paradigm where we train the systems once and we freeze it and then we transfer them to something at test time. Now, take this example of a child. Like if you freeze the brain and you stop learning, you cannot expect to generalize in this ever-changing world. So if you are like, no matter how smart you are, if you stop learning by the age of 10, you cannot function the 10 years later in your life. This is why learning in nature is kind of contrary. It is driven by continual lifelong adaptation, as we saw in the previous talk as well, by Eva as well. And this learning goes on forever. Like, this is not only about getting supervision, this is also about deciding what to learn, what tasks to learn, and continuously adapt. So the question really is, how can we formalize this idea of continual adaptation? Now, in this talk, I'll give you a couple of examples of how can we formulate this concept and how can this be relevant to robot learning. So just to start, even though I mentioned in the beginning that the goal is to learn multiple tasks across multiple environments, for the time being, just for now, let's assume that your task is fixed. Let's say you are focusing on a single task for now, and then let's study how can we adapt continuously to multiple different environments. And then we'll generalize this idea to multiple tasks in multiple environments towards the end. So for now, let's consider the task of walking. Okay. So let's say your task is fixed, it's walking. So you have to make sure that this one task works really well. But really well means it should work across every possible new environment. Okay. So this is the task. Now, so this is the work we had proposed a couple of RSS ago, like RSS 21. This work is called rapid motor adaptation. I'll go into the quickly into the key idea of this work, and then we'll talk about what are the drawbacks and how can we scale this idea. So what you see on the screen here, on the left, the robot is trained in simulation. Then on the right, it is tested on unseen scenarios in the real world, which are much more complicated than seen in the simulation. But what is happening here, the robot is able to generalize by adapting continuously in the real world. So let's look at how this model is trained at the first place. So in the beginning, this model is, again, as I said, this model is trained only in simulation. So this is it is trained in reinforcement learning. So there is a policy which takes the current state xt and the previous action at-1 and outputs the next action for the robot. And the action here is the joint state of the robot angles, or the joint angles of the robot. Now, what we want to do here, we want to train a system that can allow the robot to continuously adapt. So contrary to deep learning, where we really want invariance in the policy should work everywhere, we want the policy to be adapted to multiple scenarios. So what we do is first, we randomize a bunch of situations in simulation. So this is a very standard idea of domain randomization, where we randomize mass, friction, height, strength, etc. But usually in domain randomization or in deep learning in general, people want a policy which is robust to all these settings. But in this work, we argue that robustness is not what you should aim for. You should aim for adaptivity. So what we do here, instead of training a policy which is invariant to all these randomizations, we condition the policy on the encoding of these variables such that the policy is adaptive and not invariant. So for instance, if you're walking on a carpet versus you're walking on ice versus walking on oil, you do not want to walk the same way in all these diverse conditions. You want to know what the condition is and then adapt yourself to the condition. So here, this policy is trained such that it first knows what is the condition of the environment, the first box. It encodes that condition into this latent vector, which we call extrinsics, because this is capturing properties of the environment which are extrinsic to the agent. And then the policy is conditioned on this extrinsic, and it adapts its behavior to output the action. So this policy, as you see on the screen, is adaptive and not invariant. But this leads us to an issue. The issue is, when we deploy this in the real world, all these properties of the environment, which were known in simulation, are no longer known in the real world. For instance, I have no idea what the friction is. When I walk on carpet, I have no idea what the friction over there is, what is the height exactly is, what is the strength of the motor is, etc., etc. So if this is unknown, this leads to this unknown extrinsics, because these parameters are not in the environment. So the question is, how can we deploy this policy in the real world? So here is the idea of adaptation. The idea is, we want to estimate these extrinsics continuously online. So the robot continuously needs to update its belief of what it thinks the environment is. So how does it do that? The main insight here, we want to use the disagreement in the history of the robot to really adapt what is happening in the environment. Okay, so we use when at deployment, we use the history of the robot. The history contains two things: what was commanded to the robot and what actually happened, to predict this latent vector over here, which then guides the base policy. Now, one question here is, like this latent vector, which is extrinsic vector, it was encoded by encoding environment properties, the extrinsic environment properties. Why should the history have any idea about what should this latent be? So if you think about this, this is a very interesting connection over here. Now, if you look at the history contains the disagreement that what was commanded to the movement, the robot, and what actually happened. So for instance, if you move your hand in the free air, if I move in the hand in my free air, now my hand might move 1 unit with 5 units of torque. Now, if I apply the same amount of torque inside water, my hand will move less, right? So the disagreement between what you command to the robot and what actually happens, if there is a disagreement between that, that is usually because of the environment. So your history contains some information about what kind of environment you are in. Now, this information is not strong enough to predict the exact friction and all these values, but it is powerful enough to predict the latent vector, which encodes a low dimensional basis of these values. So just to summarize, the way this training looks is that in the phase 1, you start by training this end-to-end system using RL, which encodes its values. In the phase 2, you exactly mimic the base policy as it is, and you train a new module, which is what you call adaptation module, which looks at the history of the robot and what was commanded and what was happened. And it uses that knowledge to encode and learn this latent vector in the Z space. Then at test time, we throw away this encoder. All we use is the base policy from the phase 1 and the module, the adaptation module from phase 2, and you put them together, and then we run this continuously at test time. Now, there are many nice properties to this. Like at test time, we can run these modules separately and completely asynchronously because they were not trained in the same system. So this module can run at a slower frequency, which allows adaptations to happen, while the base policy is more like a muscle memory, which happens at very high frequency on the robot itself. And here you can adapt continuously at test time. So in the simulation, since these parameters were fixed once in the beginning, you don't need to adapt continuously. But at test time, when you're walking in the real world, this robot adapts continuously using this module. So whatever the new history comes in for the, let's say, last 2 seconds or something, you use the last 2 seconds of history to continuously adapt the Z vector. And as the Z vector changes, your base policy adapts its behavior. And this allows this robot to work in a variety of situations as we see here. So let's go into a bit more detail and try to analyze, is the adaptation really happening, or is this an artifact of a robust deep learning system? So just to visualize that, what we do, we create a difficult situation in the environment. So here we put this plastic sheet in a living room, as you see here, and then we throw olive oil on top. Here Ashish is throwing Ashish is the first of the paper. He's throwing olive oil on the sheet to make the floor more and more slippery. And then you put plastic wrap on the legs of the robot. And then we ask the robot to walk over these things. Now, if you see this video at the current speed, you can see that it has no issue walking over this sheet. But let's see this in slow motion. If you notice in slow motion, you can see how the robot continuously adapts to walk over. In fact, you can also visualize the adaptation. So here, ignore the top 2 graphs, look at the last line. So here we are showing Z1 and Z5. And you will notice as soon as the robot goes over the slippery area in the oily surface, Z1 and Z5, which are so Z is a 8 to 16 dimensional vector, and we are visualizing 2 dimensions of that vector because in this example, those 2 dimensions change the most. So here, as the robot goes over this surface, the Z vector changes its behavior to allow the robot to adapt. So the behavior goes from these high values to some low values over here. And this allows the robot to adapt its behavior. To give one more example, here we are throwing weight on the robot. A robot cannot even see the weight, but it can adapt its body as soon as the weight touches the robot. And it's very agile like an animal. So we are showing this in slow motion to really understand what is going on over here. The robot can continuously adapt in these scenarios. Now let's compare, is it necessary to adapt continuously, or can you adapt just once in the beginning? So here the robot itself, just to give a context, the robot itself is 12 kg, and we are putting 8 kg of payload on the robot. So this is like almost 80% of robot's own weight on top of the robot. So on top is our method where we continuously adapt, and you can see the robot can walk smoothly. In the bottom, we only adapt in the beginning, and then we freeze the encoding of the Z vector. So we don't adapt continuously. So what you see here, the robot walks in the beginning, but then it falls as soon as you stop adapting because the behavior stops learning. Here is one more example. Here you put a classical controller, which was robust controller on this, and on a mattress. Now this is a mattress, the robot gets confused and cannot walk. But using our approach, you can easily walk over this mattress, etc. So there's a lot of work in robotic locomotion. I'll not go into the comparison to each of these work, but I'll just highlight the key innovations and the key exciting pieces of this work. One of the main thing here is that the policy was directly outputting all the joint angles of the robot. So there was no hand-coded heuristic gate or locomotion controller in here. And with a limited amount of training and simulation, the robot was able to generalize to a wide variety of situations, as we saw in the examples. And finally, the design was asynchronous. You can run the adaptation separately from the compute on the robot. So just to go a little bit more detail into this, the first aspect, there is no hand-coded or heuristic control stack. This is in contrast to locomotion literature in robotics, where we have seen people take huge inspiration from gates in animals. Like animals show all these structured gates like walk, amble, pace, etc. And then for the last century, various models have been proposed to copy and mimic these gates into robotics through computational paradigms, starting from these. So currently, most robotic results out there rely on some sort of primitives to learn these gates or to encode these gates inspired from animals and then train these systems on top of these gates. In contrast, what we are doing is we are doing without any gate and directly from scratch, which is what gates in real life look like. So if you look at the gates in real life, they don't fall into walking, ample, trotting, and galloping. They are bouts of step which are unstructured. And this is what studies in babies and latest in biomechanics have shown us through work of Ken Adolph and Eleanor Gibson. Now, when you put a baby in a room, the gait is all over the place, and it does not fall into these categories of walking, trotting, galloping. But animals do show this gait. So there is some discrepancy in biomechanics. Why do animals have these gaits in contrast where the humans and animals show these unstructured gaits? And the difference we realize is whenever people study animals, they study them on simpler terrain when these gaits are visible. But in complex terrain, the gaits are all over the place and do not fall into this structured categories. So the interesting question here really is, why do animals even have these gaits? How can we reconcile both the frameworks together? So there are a lot of hypotheses as to why do animals show this gait. And one of my favorite one is this energy hypothesis, which argues that animals have evolved to conserve energy, and hence they show these gaits. So if you study horses on a treadmill and measure how much energy they consume on y-axis, they show different gaits at different speeds on the x-axis, and because each gait is only optimal at that speed. So at low speed, walking is optimal, at medium speed, trotting, at high speed, galloping. So what we did in our work, we also add an energy penalty on the robot. So we asked the robot to walk forward as well as conserve energy. So just by adding an extra term, our robot starts to show similar trends as that of horses from this study. Now on the left is our robot, which walks at low speed, it trots at medium speed, and it does bouncing, which is close to a gallop gait at high speed. Now, this comparison is not apples to apples because the y-axis in horses is oxygen consumed, which is total amount of energy, while in robot on the left, we are only measuring work, which is the physical energy. So we are not counting the battery energy, but the trends are very similar. And in fact, we can also compare our robot to animals using something called a Froude number, which measures the ratio of leg length to the shape. And here you can see, even though people call this robot a robot dog, but in reality, it is closer to a horse in terms of Froude number analysis. And here we can see this robot changes gaits. So at low speed, it is walking. If you increase the speed, it trots. If you lower again, it walks. And if you increase the speed again, it starts to gallop. And at very high speed, so here's an example. At very high speed, you can see it is galloping in the air. So it has learned an emergent flight phase where the whole robot stays in the air along the whole time. So some of the key questions we have been studying since this work is how do we scale this system to more complex robots? How do we go beyond locomotion? And how do we scale this to more high dimensional inputs like images? So just to study more complex robots, just locomotion is restricted. So more recently, what we have done is we have added an arm on the robot. Now, the idea is that the current existing robots, which have an arm and legs together, they are very, very expensive. Like Spot is more than 100K USD. So we built a low-cost system, which costs around 6 to 7K. It has a 3K low-cost legged robot with a 3K arm on top, which is just taped together on the robot. So it's a very low-cost system. Now, but the problem is extremely challenging. It's a very high-dimensional problem where you have to figure out how to make the robot work on this platform. Because when you add an arm with the legs, arm and legs have competing objectives. Arm wants the legs to be stable to function properly, and legs wants the arm to be stable to walk properly. So the solution in the literature has been extremely hand engineered. People design one controller for arm, one for legs, and then you put them together through another engineered system. And in this work, we wanted to study, can we scale the same idea of RMA to control this whole body altogether at once? So we applied the same idea, and it turned out it did not work. So when we scale this system exactly to a higher dimensional robot, it does not work because we made an assumption in the previous method unknowingly. And the assumption is compression does not imply predictability, or compression implies predictability. So this was the assumption. So what we were doing in phase one, we are trying to compress the environment into a latent vector. And in phase two, we are trying to predict that from history. Now, there is no reason that the particular compression encoding we are learning in phase one is predictable from phase two if we do not inform phase one about the phase two. So what we do in this work, we tied the phase one and phase two together, and we directly supervise and regularize the embedding to be also predictable while it is learning to be compressing in the phase one together. And then we apply this whole system on the whole body altogether. So here are some results. So here, this robot is controlled by a single neural net. So you can notice as the arm goes down, the legs bend automatically, the body rolls. You can notice the arm is not even attached properly to the robot. It's taped to the robot using this blue tape over here. But the single network treats the whole body as a single controller. We can apply this to even more dynamic tasks. So here we take a robot and ask it to from walking to climb a wall. And the same approach can help this robot climb a wall, which is a very dynamic task. And it can balance on 3 legs to open the door using the 4th leg. All this is controlled by a single neural network, a single deep network, which is running on the robot FPGA. So if you see this in slow motion, you can see that the robot can adapt and climb to the wall nicely. We can also adapt using vision. So far the robot was blind, and even the blind policy was very effective. You could see it can walk in multiple scenarios. So why do you need vision? Well, we need vision to walk on very challenging scenarios like stepping stones on the left. We cannot walk blind on that, or climbing stairs intentionally. But the problem, and this is a studied problem in literature, but the typical approach in the literature is to first build a map of the environment using vision, and then use that map to walk and find footsteps to walk on that in the real world. But the issue is when you are building map at such high frequency, the terrain map get very noisy. So this is the paper from Marco Hutter in Science Robotics. You can see the map they are building. They show impressive results, but if you look at the maps are quite noisy. So to deal with this noise, they have to add noise in the simulation itself. But when you add noise, it becomes difficult to do more precise locomotion, like stepping stones and things like that. So in this work, we really question, do we really need maps? Like if I ask you how many stairs are there in your apartment from your road to your apartment or a room, you will have no idea because people do not build maps at such high frequency. We have intuitive, direct sensory perception, and then we use that to perform locomotion. So in this work, we argue to tightly couple vision and control together. So what we do, we directly take vision as input and we output the joint angles altogether without building any map in the environment. So the robot sees the vision image on the top right, the depth image directly, and it directly outputs the joint angles for the robots. As you see here, this robot can perform a very complicated maneuver over here, over these stepping stones. It has no issue walking over this, and it is directly operating from its front camera. So the real legs of the robot do not even look at the terrain. They are trying to walk from memory. And here it is climbing on very difficult stairs. These are in Highland Park in Pittsburgh near CMU. And notice one thing, notice the height of stair and the height of robot. Sorry, the height of stair, okay, never mind. So the height of stair and the height of robot were almost the same, but the robot has no difficulty climbing this. So in this example, you can see the height of the stair is very high. If you compare this robot to other robots, a small robot is more like a small dog. It has very high difficulty in both climbing and declimbing the stairs. But since we are outputting the joint angles directly, we see a new gait emerge in the robot where the robot uses the hip joint of the legs to create this abduction-adduction behavior to climb this high stairs. So if you can see here, the robot climbs stairs similar to how humans climb walls, because the height of the stair is similar to height of robot. So how human climb hurdles, robot climb these walls or these things. And it also has emergent foot planning behavior. So here the robot is operating in a variety of situations, both outdoor, indoor, and all these scenarios. And we also compare to a variety of baselines, and the result, the difference between map-based baselines and our method is not much in simple environments. But when you look at the complicated environments like stepping stones, the difference is huge between building a map and not building a map. And we have been also doing live demos of this robot. This was in Coral 6 months ago, and it was in CVPR last year in the Marine Park. So I'll stop here and take any questions. But let me just quickly. Oops, sorry. Sorry, my slides got hanged. Try to. Just a second. So we have also scaled this work beyond quadrupeds to even bipeds, and here you can see a biped robot walking in difficult situations. I don't have time to go into more things right now, but we can also scale these ideas to go beyond locomotion and also perform manipulation by watching humans. So here you can see a robot performing different manipulation tasks by watching human in multiple environments and performing. I don't have time to go into this, but feel free to check this out on my webpage or other talks at RSS I'm giving. But I'll stop here and take any questions that people might have. Thank you.